or at a temperature below the critical point, when we start performing this experiment on a constant temperature, as we said, we start from the pressure, which is very high, where we make sure that the system is all liquid. And then as we remove mercury from the cell, as we remove mercury from the cell, the liquid expands, and at what one point the gas starts coming out of the liquid. When the first gas bubble comes out of the liquid, we call that bubble point pressure. And then if we continue removing mercury from the cell, which means we are continuously expanding this liquid, more liquid converts to the gas. And then at one point, when the last droplet of the liquid goes to the gas phase, which we call it dew point pressure, the system becomes gas. And after that, the pressure starts dropping. So the behavior of the pure substances is when we have the pure substances, as we drop the pressure, the liquid expands. But when we reach to the bubble point pressure, where we have the first gas bubble, till the dew point pressure, where we have the last droplet of the liquid, the pressure stays constant. And the only thing happens by removing mercury from the cell and expanding the system is more liquid converts to the gas. Okay. This pressure, the bubble point pressure, is equal to what we call the vapor pressure, and that's equal to the dew point pressure for pure substances. Because as we said, the pressure will stay constant from the time that the first liquid droplets, first gas bubble comes out of the liquid till the last droplet of the liquid goes to the gas phase. Okay? So this experiment can also be done at a temperature above the critical temperature. So if the temperature is above the critical temperature, then what happens, we are at 0.4, okay? The system is all at liquid. We pressurize the system is at the liquid. And then when we start expanding the liquid by removing the mercury, so we will have the liquid expanded, and at one point suddenly all the liquid goes to the gas phase. So we will not see any two phase or any liquid and gas coexisting at the same condition. Okay, so in the case that the temperature is above the critical temperature, okay, as we said, or the pressure is above the critical pressure, as we said, we cannot have pressure and we cannot have liquid and gas coexisting. So the system starts with liquid, but when we expand the liquid, at one point the whole liquid converts to the gas. As I said before, this experiment can also be done at a constant pressure, but we usually do it at a constant temperature. You know, the concept is the same. We start from one end and then we start increasing the temperature till the first gas bubble comes out. As you increase the temperature, the liquid basically expands, you know, and then the liquid expands, the volume goes up. At one point, you will have the first gas bubble, and then when you have that first gas bubble, the temperature will stay constant till you convert all the liquid to the gas, and after that the temperature will change. Okay, so that's the same concept but at the constant pressure. So again, here what we do, we keep the pressure constant, we change the volume. As we change the volume, the temperature will change. Okay, so when we increase the volume, the liquid expands, okay, and the temperature goes up, and then at one point gas comes out, and then if you continue doing that, more liquid converts to the gas, and at the end we have all the gas phase. Okay, but as we said, this is very hard to perform this experiment for every single component, because you have to do this to get the whole vapor pressure line. Okay, you have to perform this experiment at multiple times, okay, at multiple temperatures, and then every time you have to do this, and you have to get some points, couple of points in the liquid phase, couple of points on the vapor pressure line, and couple of points in the gas phase, and to be able to generate the whole pressure, temperature, or phase diagram for the pure substance. It's very time consuming, so people, they try to come up with the relationships, the equations that can describe this behavior. Clausius and Clapeyron, they introduced the equation which says the derivative of vapor pressure with respect to the temperature, dPV over dt, is equal to the LV, which is the latent heat of vaporization, over temperature times the molar volume of gas minus molar volume of the liquid. Okay, we'll go over these definitions. The molar volume of gas is basically the volume of 1 mole of gas. Okay, so they generated this. They wrote this equation, and then uh, what they did to, because in this equation you have pressure, you have temperature, you have volume, you have all the components. So to make this simpler, this equation, to be able to come up with some sort of a relationship, what they did, they said, okay, we are going to assume that the molar volume of liquid is negligible in compared to the molar volume of gas. So basically, 1 mole of molecules, 1 mole of gas has much higher volume than 1 mole of liquid. Okay, which makes sense. The same number of the molecules in the gas phase generates much higher volume than the same number of the molecules in the liquid phase, because in the gas phase the molecules are further away from each other, it's expanded, but in the liquid phase they're much closer to each other. So the molar volume of gas is much higher than the molar volume of liquid. But this is only valid if you are away from the critical conditions, if you are away from the critical pressure and critical temperature of the system. Okay, but they assume that, so they assume the 1 mole of gas has much higher volume than 1 mole of liquid. Okay, so they drop the VML. So in the equation 2.2 we don't have the VML. And then what they said we also assume that the heat of vaporization is a fixed number. It's not changing with temperature. Again, this is an assumption that they made. Why they made that assumption? Because they wanted to take the integral of this equation. Okay, and then what they said we're also going to use the relationship, which we call it the ideal equation of a state, which we will go over it, in a few slides. And that relationship is saying that the vapor pressure, or pressure times volume, is equal to the constant times temperature. Okay, so PV is equal to RT. Okay, pressure times volume is equal to R, which is a constant, times the temperature. They use this general relationship, between these pressure, volume, and temperature of the pure substances, and they replace the volume of 1 mole of gas with this equation. So from this equation, Vmg, which is the volume of 1 mole gas, becomes RT over PV. So if we replace the RT over PV instead of Vmg in this equation, then the equation becomes dPV over dt is equal to vapor pressure times LV over RT squared. So in this equation now we only have pressure and temperature. And as I said, since they assume the LV is a constant, the heat of vaporization is not changing with temperature, R is a universal gas constant, so they can come out of the integral. So if we take the integral of this equation with respect to pressure and temperature, so dPV over PV, the integral of dP over PV becomes the natural log of PV, and the integral of LV over R of 1 over T squared becomes minus 1 over T. Okay, so they took the integral of this equation, and then they come up with the final form, which says the natural log of PV2 over PV1 is equal to LV over R times 1 minus T1 minus 1 over T1 minus 1 over T2. Okay, so now we can see that the pressure, PV over PV, PV2 over PV1, so that's the pressure. Natural log of that pressure has a linear relationship with 1 over temperature. Okay, so PV2 over PV1, that's a pressure component, and 1 over T1 minus 1 over T2 is a temperature component. So the natural log of pressure has a linear relationship with 1 over temperature, because LV is a constant, they assume it to be constant, or R is a universal constant. So they said if we plot the vapor pressure, the natural log of vapor pressure as a function of 1 over temperature, we should be able to get some sort of a straight line, okay? And with this straight line now, they can infer the vapor pressure of the components at different temperatures, okay? So, for example, this is the vapor pressure of normal hexane plotted in a semi-log graph. But people, they have done more study on this, and using this Classis and Clapeyron as a basis, they come up with the graph which shows some sort of a temperature versus pressure diagram, temperature versus pressure diagram for all the pure components. Okay, so this is not a semi-log graph. This is a specific graph that they have been using, and it has been called the Cox chart. And remember, we are going to use this Cox chart from now till end of the semester. This is a very important chart, which basically gave us, which can give us the vapor pressure of all the pure components and non-hydrocarbon components at any temperature. So basically, at any temperature, we can read the temperature from the y-axis, and then we can draw the line and then read the pressure of the vapor pressure of the pure components, okay, associated with every temperature. So we will get the vapor pressure of the pure components using the Cox chart. And as you remember, we said for all the pure components, the vapor pressure will be equal to the bubble point pressure, and that's equal to the dew point pressure, because that's the behavior of the pure components. When we hit the bubble point pressure, the pressure will stay constant till we convert all the liquid to the gas. That's the dew point pressure, and that's equal to the vapor pressure. So every time that we are interested to find the bubble point pressure or dew point pressure of the pure substances, we can use the Cox chart. That gives us that pressure at different temperatures. There are other graphs that also we are working in the oil and gas industry, and one is the pressure versus volume. Okay, it could be pressure versus a specific volume. It could be pressure versus 1 over volume. It's just a pressure, some sort of a pressure versus some parameters related to the volume. Okay, and we call it PV diagram. In the PV diagram, again, we do this at a constant temperature. So the temperature is constant. Okay, and we are looking at the pressure versus some sort of a volume parameter. In here, basically, it's a specific volume. So if we start with from a very high pressure, let's say 0.1, by slightly increasing the volume, okay, the pressure will significantly drops. Okay, that's a property of the liquids. So the volume of the liquid is very sensitive to the pressure of the liquid is very sensitive to the volume. Okay, small change in the volume of the liquid will result in huge change in pressure. Why? Because the liquids are not compressible. Okay, we are using this behavior in the hydraulic brakes. You push, in an old car, when you had a hydraulic brake, when you push a brake, you change slightly the volume of the liquid, but it generates a huge pressure that can be used to stop the wheel. Okay, so this is one of the properties that we also use in the labs to apply some sort of confining pressure to the sample. We use the hydraulic pumps because very small change in the volume of the liquid will result in a huge change in the pressure, so we can apply huge pressure on the samples.